All right, we are still looking at the solutions for test review number 3. I'm going to say this is part 2, problems 12 through 18. And problem number 12 wants us to tell whether the sequence B sub n converges or diverges. So if we want to tell whether a sequence converges or diverges, this just means that we want to find the limit as n goes to infinity of that sequence. So we're going to set up the limit as n goes to infinity of 3n to the 4th plus 2n cubed minus n squared plus 8 divided by 3n plus 2n to the power 4. Now you may immediately be able to tell that we are finding a limit as infinity of a rational expression, and in the case where the degree of the top is equal to the degree of the bottom, we know the limit will simply go to the ratio of the leading coefficients. But we can take a minute and prove that using L'Hopital's rule. So if we simply plug in this limit, we see that we get infinity over infinity. So we're going to use L'Hopital's rule. So this will be equal to the limit as n goes to infinity of 12n cubed plus 6n squared minus 2n over 3 plus 8n cubed. Again, we get infinity over infinity, which means we'll use L'Hopital's rule once more. So we have the limit as n goes to infinity of 36n squared plus 12n minus 2 over 24n squared. So again, we have an infinity over infinity form. So once more, we will use L'Hopital's rule. And so we finally end up with the limit as n goes to infinity of 72n plus 12 over 48n. Again, this is infinity over infinity. So one more iteration of L'Hopital's rule gives the limit as n goes to infinity of 72 over 48, which we know is simply equal to 3/2. So we can say that this sequence will converge to 3 over 2. In number 13, we would like to tell whether the sequence a sub n, that is equal to n squared over the natural log of n, converges or diverges. So again, I will set up the limit as n goes to infinity, and we see that this limit again is equal to infinity over infinity. So once more, this calls for L'Hopital's rule. Derivative of the top, derivative of n squared is 2n. Derivative of the bottom, derivative of natural log of n is 1 over n. Before I actually plug in this limit, I am going to make a simplification here. 2n divided by 1 over n, if we flip and multiply, or multiply by the reciprocal of that denominator, we get the limit as n goes to infinity of 2n squared. Now when we plug in infinity for n, we can see that this limit goes to infinity. So finally, this sequence will diverge. Number 14, we have the sequence b sub n, that is cosine of n times pi divided by n to the power 4. So we will set up the limit as n goes to infinity of 1 over n to the power 4. And we see that's equal to 0. So what happens here is we're going to drop the alternating component. That cosine of n times pi is an alternating component. If we drop that, we see that the limit goes to 0. So that means with the alternating component, the limit will most definitely also go to 0. The alternating component is just going to help that limit converge even faster. Another way to look at this problem is to just write out the first few terms. So if we start just writing out the elements of this sequence, we see that this will be negative 1 plus 1 over 2 to the 4th, minus 1 over 3 to the 4th, plus 1 over 4 to the 4th, and so on. So we see that the value of these elements are approaching 0 very, very quickly. So therefore, this sequence converges to 0. Number 15, we would like to determine whether the geometric series, the sum as n goes from 1 to infinity, of 4 over 5 raised to the power n plus 1, converges or diverges. All right. So first of all, we want to compare this, and we see that right now this is a sum that's in the form of ar to the power n plus 1. We really would like to have this to be the sum of ar to the power n minus 1. So what I'm going to do is I'm going to basically pull 2 units off of the base number 4 over 5. So we could write this as the sum in going from 1 to infinity of 4 over 5 squared times 4 over 5 to the power n minus 1. This would be an equivalent way of writing the expression. And now it is in the correct form. I have my sum starting at 1. This is now in the form a times r to the power n minus 1, which is the correct form. So we can read off here, absolute value of r here is 4 over 5. Since that is less than 1, the geometric series test says that this series will converge. It also tells me that it's going to converge to a over 1 minus r. So that will be 4/5 squared divided by 1 minus 4 over 5. This is equal to 16 over 5. So this series converges to 16/5 by the geometric series test. All right, problem number 16 also provides me with a geometric series, but this time in its expanded form. So that means in its term-by-term form. 5 plus 5/3 plus 5 over 9 plus 5 over 27, etc. So the first thing that I need to do is to rewrite this geometric series in its sum form so that I can be able to apply the geometric series test. So we see in the numerator, we just have the constant 5 each time. In the denominator, we see powers of 3. So I'm going to write this as the sum, n going from 0 to infinity, of 5 divided by 3 to the power n. Of course, you can also write this as the sum as n goes from 1 to infinity of 5 divided by 3 to the power n minus 1, if you wish. But this could be cleaned up. This is in the form, the sum n going from 0 to infinity of a times r to the power n. I'm just going to write this as the sum as n goes from 0 to infinity of 5 times 1/3, quantity raised to the power n. Just so that we can very clearly see that a here is equal to 5 and r is equal to 1/3. So here, since my r value is 1/3, that is less than 1, we know the series will converge. And if it converges to a over 1 minus r. So for our problem, that's going to be 5 divided by 1 minus 1/3. This is equal to 15 over 2. So this series converges to 15/2 by the geometric series test. All right, number 17 wants us to determine whether the telescoping series, here we have the sum going from 1 to infinity of natural log of n divided by n plus 3, converges or diverges. So the first thing I'm going to do is just expand that logarithm. Natural log of n over n plus 3 can be written as natural log of n minus the natural log of n plus 3. And so in order to use the telescoping series, I'm going to need to write out the first several terms of this series. So if we just start plugging in, when n is equal to 1, my terms will be natural log of 1 minus natural log of 4. When n is equal to 2, my terms will be plus natural log of 2 minus natural log of 5, and so on. So I made this list, let's see, I wrote 1, 2, 3, 4, 5, 6, 7 terms. You can make the list a little bit longer if you need to, but here's what I want to see. If we start canceling terms, we see that natural log of 4 and negative or minus natural log of 4 will cancel. We have natural log of 5, that's going to cancel, natural log of 6, natural log of 7, and if we just keep making the list longer, we've already spotted 2 terms side by side that cancel out. I know that the remaining terms are going to cancel out if the list just keeps getting longer. However, we see the terms natural log of 1, natural log of 2, natural log of 3 right here at the beginning that are not going to cancel. So let's quickly see what happens to the terms at the tail end. Minus natural log of 8, minus natural log of 9, minus natural log of 10. Again, if we just keep making the list longer, what happens to those terms? Well, here's what happens. Essentially, as n gets bigger, the limit of these terms, minus natural log of n plus 3, will kind of just keep increasing and increasing and increasing. So they do diverge to negative infinity. Unfortunately, they do not converge. So I can't just discard these terms. And because they diverge, the uncancelled terms diverge, we are going to say that the series in general will diverge by the telescoping series test. So number 18 is another telescoping series test. Here we have the sum n going from 1 to infinity of e to the negative 3n minus e raised to the negative 3 times n plus 1. So I'm going to just clean that up, and I'm going to write this as the sum of 1 over e to the 3n minus 1 over 3 times n plus 1. And again, I'm going to write out the first few terms of the series. So this will be 1 over e cubed minus 1 over e to the power 6 plus 1 over e to the 6 minus 1 over e to the 9 plus 1 over e to the 9 minus 1 over e to the 12, and so on. And again, really quickly, we see that terms are going to start canceling. So the 1 over e to the power 6 terms cancel, 1 over e to the 9, 1 over e to the 12. And so since I have consecutive terms canceling, I know the remaining terms will also cancel if the list gets long enough. So I have two terms that I need to decide what happens to these guys. The first one, the 1 over e cubed, is not going to cancel, so we're going to keep track of that guy. But the term at the very end, the minus 1 over e to the power 15, if we make the list long enough, so as n goes to infinity, we see the limit of these terms at the tail end go to 0. So eventually they will all converge to 0, so their value is not going to contribute to this series. So since the uncancelled terms converge, we can say that this series converges to 1 over e cubed by the telescoping series test.